Welcome back. Now, in this case we are able to look at hydrocarbon potential, and we know there are different elements to it. So, let me revise it very quickly. We heard that there is bond stretching. We understood that it is based on essentially stretching of the bonds. Then we look at bond bending, where it is the in plane bending angle theta, and k theta is essentially the bond angle that it is. And then there is a out of plane rotation, which you are looking at here, k phi, and that phi is the one which is the spring constant or potential constant for the rotation, and cos n phi is the rotational angle. So, if you combine all three ideas, then you have bond stretching, bond bending, and bond rotation. All of these together, then you have two parts to it. One we call bonded and non-bonded, and the non-bonded is the Leonard-Jones type and electrostatic point. So, this really gives you good idea about how now we can construct for larger molecules. Now, this is very simple to understand. So, now let us look at a simplistic 3 atom molecule called water, and water obviously we will look at both ice phase and the water phase. So, in this case if you look at these large blobs, these are two oxygen atoms, and these oxygen atoms are connected by a hydrogen bond in between, but there is a intra. So, we are looking at UIJ intra between, and intra works between oxygen and oxygen, and inter works between oxygen and hydrogen. So, we are only looking at this oxygen ROO, this part. So, if you look at this ROO, then you can look at again using Leonard-Jones model, and this is the Coulomb model. You can now look at that, and you have both formulated Leonard-Jones part as well as the other one. So, now you are looking at some of the comparison of potential functions of this kind by again empirically doing lots of experimental fitting of these forms of mathematical forms to get the right kind of force model. Now, if you look at here, you can also look at S, R, I, A and J, B. We are looking at some cutoffs here. If it is less or equal to I, A, J, B, then it is 1, and if it goes beyond that, then there is an exponential decay term which is put here. With that understanding, now we look at a simple point charge potential that I personally worked on for many years in terms of the ice and water interaction with the metals, and how they formulate a ice layer on the aircraft wings, for example. That was one of the practical problems that we looked at, that when aircraft takes off, especially in the cold weather, there is a thin layer of ice is formed at the leading edge, and that changes the aircraft's wing shape. And once the wing shape goes to a very different kind, then aerodynamics completely changes, and then lot of accident happened earlier when people did not understand that icing of the aircraft wings can cause planes to take off to a certain extent and then fall off. And so, there were a lot of accidents earlier, but and that is why in the winter time before any aircraft takes off, they do de-icing. And I am sure you must have waited many times to your plane to be de-iced before it goes to the next station. And that de-icing came because of the understanding of this kind, where we looked at when the water molecules very low temperature, they hit the surface aluminum surface of aluminum alloy surface of an aircraft wing, then how do they formulate a thin layer of ice, and what is the adhesion of that. So, without going into that detail, which we will talk later on in this course as practical examples of it and how we solve that problem of de-icing, we are going to look at here just in terms of the potential functions inter and intra. And this is simple point charge potential which was created by Tukan and Rahman, and these are the famous scientists who worked all most of their professional lives in order to generate some very interesting potential function models, which we will talk about. So, this is the water potential. So, in this case we are now going to first look at the inter part and then the intra part. So, what we are looking here is that the interatomic potential, we are looking at Qi Qj, and oxygen potential, and then we are looking at the DOH, the bond length between OH and HH and HOH angle, bond lengths, etc. And these are the parameter. A is the parameter given here for the Lennard-Jones part, C is the potential part for Lennard-Jones. We are also looking at the charges 0.82 electron volt and 0.41 electron volt, and if you look at the A is 629 0.4 10 to the power 3 kilocalories per mole per angstrom. So, we are looking at all these parameters that have been experimentally fitted, and now we get into the bond length. So, there is the equilibrium bond length is 1.0 between OH. The equilibrium bond length between HH is 1.6337 angstrom, and then the angle between the two hydrogen and oxygen 109.47 degrees. So, these are experimental parameters, and then there are also parameters for intramolecular interaction. So, you are looking at all these different intramolecular interaction between OH, the density, and the sigma is coming out of the lattice parameters and the density based on that, and then k theta, and these are the spring constants which are for all these three interactions that we looked at. So, you can simulate bond stretching. So, delta R1 and R we are looking at equilibrium EOH, delta R2, and again with this is the second hydrogen atom connected with oxygen, and then we are looking at HH. So, this is, you can think about a triangular molecule where the two sides are OH of 1.0 angstrom, and the third side of the triangle is 1.6337 angstrom. So, with that understanding, you can see now I am going to show you another water molecule simulation here. So, you understand how the intra and inter will now interact between oxygen and oxygen and hydrogen 1 and hydrogen 2. So, let us get to our familiar VMDL. So, now let us look at this water molecule system, and because we are looking about bonded potential functions. So, we give it a try. Let us go back to the mixed model. Now, you can see it more clearly, and you can see on the right hand side that potential energy curve for equilibration. This is the kinetic energy term in equilibration, and then let me zoom. So, you are looking at the bonds here at very low temperature. Let me stop it and change some parameters. So, let me give some temperature here. Let us keep it below the melting temperature. So, we do not see some breaking. Density will keep the same. Now, you can see the motion of these different bonds. So, now if you look at this oxygen atom, which is the white, and the red ones are the hydrogen, you can see how they are represented. In this case, this is intra between oxygen and oxygen, and this is inter, which is between oxygen and oxygen here, and the intra is between oxygen and hydrogen. So, inside the molecule is intra, and between molecule is intermolecular system. So, if you look at here, if you follow that one hydrogen atom is between two oxygen, which is creating the hydrogen bond, the famous hydrogen bond that you hear about. This is what is the simulation of that. So, now you can see the interaction when you are calculating using, let us say, point charge potential function that I use in my studies. You can see that these are very nicely defining the action, and this is still in a solid phase, and you are able to look at how the solid phase goes in here. So, now let me go forward and stop that and increase and see what happens to intra atomic interactions. Now, you can see immediately it is increasing. So, let me spin it a little bit. And we are looking at the evolution of kinetic energy on the right hand side. This is the total energy. In this case, volume is constant. pressure is fluctuating, but almost constant. Potential energy is changing. So, if you look at it is minus 3.6, and because we have given it temperature. So, let me stop it here and then give more temperature. So, this is already gone way above. So, we are now going to look at the gas phase as the bonds are completely breaking down and potential energy is climbing up, which is indicative of some of the transitions that are taking places between the atoms. Now, one thing you need to observe as we are rotating through it, let me stop it here. If you look at the water molecules, some of them are completely free, but as they come close, they do form a hydrogen bond between them. So, there is some local order, while it is completely becoming disordered with the temperature. So, if we now go back, stop it here and then go back to very low temperature again, and so this is the simulated annealing, we are quenching it, and now we will watch what happens to the system as it freezes into different phase. So, you saw potential energy has gone down quite a bit, and this is the transition that you will observe, because the potential energy is way down now, and this is a jump in the potential energy. And let me zoom out. You can see now they are frozen, and let me look at different angles. So, now you can see how different parts of the atoms are looking like. So, let us look at the front view. Now, let us look at the side view, and so these are the, you can see that it is not going back to tetrahedral coordination. So, these areas have certain coordination, but here is hexagonal structure which is being created with 6 oxygen atoms roughly, and this is gone to very low temperature now. So, this is freezing again, but not going back to the crystal structure that we started with. So, let me stop here. And let us see if I say restart it. So, in this case we can look at the top, then we can look at the left, and then we can look at the top view. So, you can see these 3 views, and we can start again at different temperature. So, the point here what I was trying to make is the intra and intermolecular potential function that allow you to simulate a complex system like water, and then you have to observe that the anomalies that you observe in water, that the water density goes down as it freezes. You have to observe that in simulation and make sure that that simulation model with Toucan and Raman potential or ST2 potential, there are about 15 different potentials for water simulation, whether they follow that and what properties they are able to follow correctly, and those are the properties that you will look at. The Toucan and Raman potential, the reason I took, because we are looking at vibrational properties, and that potential did very well in the prediction of the vibrational models. Thank you.